Welcome to the 1973 Nobel Prize in Physics, which I'm going to call the Quantum Tunneling Prize. Now, this prize was split between three people, but it was really divided. So one half of the prize was split evenly between Leo Esaki and Ivar Giaever, who's from part of Europe, and I'm pretty sure I butchered his name, and I apologize. But they won for their discoveries regarding the tunneling phenomena, which plays a role in both semiconductors and superconductors, quantum tunneling. The other half of the prize went to Brian Josephson. He won for his theoretical predictions of supercurrent through a tunneling barrier, and this has become known as the Josephson effect. Now, that's why we're calling this one the Quantum Tunneling Prize, because it explains a lot of things that go on down at the quantum level. Now, that's a whole lot of words that we all understand all the words, but hearing them in this order makes it a little bit crazy, right? Now, in a classical sense, you could think of tunneling like you're trying to roll a ball up a hill, but you didn't give it enough energy to get to the bottom of the hill, and gravity overcomes it and makes it roll back down. But for some reason, the thing still makes it over the hill. That's what quantum tunneling is. You've got this barrier in front of you. You don't have enough energy to get over it, but somehow you manage to make it across. And this is really because of the wave particle duality of things when you get down to the quantum world. So all this is done with electrical potential instead of gravity and kinetic energy, but the same basic effect applies. And things besides Ant-Man do exist down at the quantum level. So let's dig in a little bit more and try to understand really what this is. But basically, remember, at its heart and soul, what this means is that you can pass a current through something that the current shouldn't be able to pass through, and it still goes across. It's because of superposition. There's a funny wave phenomena thing called superposition that allows this to happen. But it does happen, and it leads to some really interesting effects. So let's dive in a little bit. Now, like I said, down at the quantum level, you can describe things as both waves and particles and Ant-Man. Just kidding about the last one. But this duality allows the particles to do all sorts of interesting things, like we talked about, going through those barriers when there's not really enough electrical potential there to get them across, but somehow it still passes. Now, what Leo Esaki did was he demonstrated that tunneling effect in semiconductors, and that led to this thing called tunneling diodes. And a tunneling diode is a little gizmo inside some electronic circuits that essentially has a negative resistance. And what that allows you to do is it allows you to use that quantum effect to build an amplifier for your electric circuit, which is a pretty cool little gizmo. I've used them in a lot of lab experiments, and they exist in things you have in your home. If there's more of these used than you would actually believe. They are all over the place. They used to be in radios and TVs, and now we do a lot of that with cable, but or internet. Actually, it's all streaming now. But these things were vital in some early electronic circuits, and they're still used all over the place today. So tunneling diodes, when you see those or hear about those, if you ever took a basic electronics class, what they were talking about was quantum tunneling. It's pretty cool. You got to use quantum mechanics. You didn't know you were really doing it, which is the best kind of invention. But that was Leo Esaki. He was the guy who came up with the first one. And the dude's still kicking around. He's 99 years old, but he's still alive today. So let's dig into the next part of this prize. Okay, Ivan, and I am not going to try to pronounce his last name again because he's Norwegian and I would get it wrong. In 1960, he did an experiment, which was a tunneling demonstration through a very thin layer of an oxide material, and it is down at superconducting temperature. So what he basically did was he built a superconductor out of this oxide and things that weren't normally superconductors. But what he was doing was he was demonstrating this tunneling effect. So some things are just natural superconductors. Other things you have to kind of create a superconductor. And what he did was he set the ideal conditions to allow that quantum tunneling to take place. And this is a huge deal. Even today, this is a huge deal because if we're ever going to get to higher temperature superconductors that are going to allow us to use these applications on a much larger scale, rather than just in laboratories and hospitals and places where you have lots of equipment around, it's going to be because of this effect, this oxide effect, this Josephson effect that he was the first one to demonstrate. That's going to be what enables that technology. And this was the very first time that was seen. And this is probably someday going to lead to a much higher temperature superconductor that's going to see widespread application. And I think that's really cool. But and he's still around. He's in his 80s and he is still with us. So the very first one of these that was sort of this manufactured superconductor in a way that wasn't just a mix of different materials. This was the guy. Here it is. Now, let's dig into the theory part of this. So these two guys with the experiment, remember, sometimes you can have an experiment, but you can't explain it. And the Nobel Committee likes to have both the experiment and the explanation. So let's dive into the other side of this because now we have to explain how all this stuff works. That's always the fun part. Now, Brian Josephson, the theorist behind all this mess, the two experiments we talked about basically proved the DC direct current and the AC alternating current applications of what is now become known as the Josephson effects, which explains all this quantum tunneling stuff. When electric current passes in DC, in the DC case, when electric current passes through a Josephson junction, you can get a flow without any voltage going across that junction. So once you get it started, it kind of keeps going. This is from that tunneling of what are known as Cooper pairs, which are pairs of electrons through a barrier, even if they should not pass through that insulator. So you got an insulator trying to stop them, and they go through it anyway. That's because of this Josephson effect that we see. In the AC case, if a voltage is applied through a junction, a supercurrent will oscillate. You'll get this frequency of oscillation, which sometimes is very important, depending on your application. Because without it, we wouldn't have microwave ovens, which are not done by quantum tunneling. They're done by resonant cavities, but same thing. You have to have an oscillator. Now, AC, if you apply a voltage across a Josephson junction, you get a supercurrent that oscillates at a frequency proportional to that voltage. This is used for very highly specific and precise voltage standards, which are useful in a lot of both laboratory applications, big industrial applications, all need these standards. Now, the apps for this trio, these three guys kind of got together and did all this work, and the applications that have come out of that work are pretty interesting. All kinds of something called SQUIDs, which are superconducting quantum interference devices, which allow you to do a lot of really interesting work down at the quantum level. Voltage standards, which are important for all kinds of industrial applications. You got to have them, and what I think is going to be the coolest one, certain qubits for quantum computing are actually based on this Josephson effect. And I think those qubits are going to be the ones that eventually see application. Now, quantum computing is a whole thing all by itself. And when I say qubits, when you hear about a bit in a computer that's like a 0 and 1, a qubit is much different. Quantum computers can not just store zeros and ones, they can store anything from 0 to 1 and an infinite number of states in between them in a qubit. So are a whole different beast. But they are sort of the future of computing, or it's supposed to be if they can ever fully become available. They're not yet. We're getting there, but they are centered around these things called qubits, which are based on this Josephson effect. At least some of the qubits are. There's other qubits based on other effects. Some of them are based on this. So we may eventually see this same effect come back again in the quantum computing world, and who knows, could lead to another Nobel Prize. But that's these three guys. A great trio. All three of them are still with us to this day. I hope you've enjoyed this video. Please don't forget to click subscribe and like and all that fun stuff that helps us out with the algorithm. And we'll see you on the next one.